Yes, perhaps. Yeah, I think you don't know the oxygen budget is a lot of work and should be like water. Okay, so you can have it or like super early.
Welcome to the second morning session. Here we have Caroline, who will be talking about GJ9827D.
Just give me a second.
Oh, yeah. And here's a clicker if you need.
Are people hearing me all right? No, I feel like I'm not doing anything with the microphone.
You should turn it on first.
Oh, this is an interesting idea. Okay. Green is good. Okay. Now let's see if I can find a spot. Okay, can you? I feel like you're not hearing me through the microphone. Am I not speaking to the? Oh, now you are. Okay, so it just needs to be real close. Okay, yeah. Well, if people online should say if they don't hear me, I feel like it's working now. Okay, awesome. So, hi everyone. I'm Caroline Piaulet Ghorayeb. I'm a postdoctoral researcher at the University of Chicago. And today, I'll try to convince you that even if this conference has been all about rocky planets, there's actually a lot that we can learn about the ingredients that it takes to have atmospheres on small rocky planets by looking at small sub-Neptunes. So this question of whether small rocky planets actually have atmospheres has been central to this workshop. We've seen 100 different versions of the cosmic shoreline diagram, but basically the question is there something that we can learn at the population level by figuring out which small rocky planets have versus don't have atmospheres? And fundamentally, that depends on a few factors related to the formation and evolution of those planets. First, how much volatiles they actually started out with. Second, how much irradiation they received from their host star and how that affected atmospheric loss and whether they were able to retain any atmosphere. And finally, to kind of counteract this loss, you can shield some of your volatiles in the interior or also outgas them over time and potentially revive atmospheres. And what I want to argue is that all of these important processes also sculpt the small sub-Neptune atmospheric compositions. They start with also certain amounts of volatiles, which compared to the larger sub-Neptunes or even the gas giants, their volatile content should actually have potentially a measurable impact on their atmospheric compositions because they're much thinner. Then, as they start very hot, a lot of their volatiles can be into a molten magma phase, but there will be these long-lived chemical interactions between the interior and atmosphere of the planet, where we can learn about some of the interior's properties. And over time, as the planet cools down, and maybe even the magma ocean may solidify, they're further sculpted by these mass loss processes, and that could even lead to compositional evolution as well, as you lose preferentially lighter species. But the interesting thing about small sub-Neptune is that just from their density alone, we know that there is an atmosphere to speak of and to potentially characterize with telescopes such as JWST. So all of this as a motivation to talk again about one of my favorite sub-Neptunes, GJ98270. So it is a 2 Earth radius sub-Neptune. It's the smallest one that we have measurements of atmospheric composition for. And what's really interesting is it's really on the cusp of the radius valley. So if it had a hydrogen-rich composition, you should expect to see a lot of atmospheric escape. But for the audience of this specific conference, what you could also think about is that in terms of its mass, it's actually quite similar to a lot of the rocky planets that we're interested in. And so for formation building blocks, the mass budget that it was working with could be similar to what has led to the formation of some of the rocky planets. And so what we know so far about this planet has been sculpted by observations up to about 2.8 microns with JWST and HST. And so what we've seen is that there is water absorption throughout its near-infrared spectrum. But this is one of the best sub-Neptunes for characterization. These are extremely small water features. And what that told us at the time is that actually hydrogen can't be the dominant constituent of the atmosphere. It has to have a metal-rich composition. Now, that doesn't mean that water is actually this dominant constituent. It could be other things like carbon-bearing species. But with the wavelength range that we're covering, we weren't actually sensitive to those. And the other thing that also kind of builds into this picture of a metal-rich atmosphere is that there were searches for Lyman alpha absorption, helium absorption from the ground and from space, and there was no evidence of absorption to speak of, while hydrogen-rich atmospheres would be extremely unstable because of the low density of this planet. So what I want to argue is here that there's a lot of value that can be gained in the understanding of planetary building blocks, especially for these small sub-Neptunes, by looking for carbon species. First, when you have a metal-rich planetary atmosphere, you're looking at temperature as a function of pressure on this plot here. Metal-rich atmospheres are actually hotter. And so potentially that can help sustain a magma ocean, so an interface between the atmosphere and the interior where you can have effective chemical exchanges over long periods of time. And that will actually affect how good you are at estimating your bulk volatile inventory from just the atmosphere observations. Because let's say you have a certain atmospheric composition on top of a solid mantle. Well, you could say that a lot of your volatiles, at least those that are not trapped in the deep interior, you can learn about from the atmosphere observations. But now if instead the mantle is molten, because of the much higher solubility of water compared to any other carbon compounds like CO2 or methane, you actually expect to maybe have 80–90% of the water dissolved in the interior as long as the molten layer survives. While for carbon species, this is orders of magnitude less. And so, well, here I put a little CO2 over there. In typical simulations, you have like less of a % of your total CO2, for instance, that would end up in the mantle. And so potentially, these are better markers of your global volatile budget when it comes to what you can learn from atmosphere observations. And so this is why this was one of the motivations for going for the longer wavelength range where we could actually probe those species for GJ98270. So we obtained 2 transits with near-spec G395 last year. The transits are relatively well behaved. There's a little bit of stellar activity to speak of, but nothing very worrisome. And just before I show the results, I want to kind of speak at the high level of the different scenarios that we're trying to tell apart here. The first one would be the planet has small features, high metallicity, but it's actually all water. It somehow has a water-dominated atmosphere. It's maybe hard to explain if it has a magma ocean, why you're seeing so much water in the atmosphere. And so in that situation, you would expect to just see water features throughout and to have upper limits on your abundance ratios of carbon species to water. On the other hand, if it actually formed oxygen-rich but with some amount of carbon, C/H ratios that are reasonable for sub-Neptunes, then you would expect to actually see a prominent CO2 feature. And perhaps SO2 if you have photochemistry playing a role. And finally, and perhaps less likely, since we're already seeing so much water in the atmosphere, it could also have formed oxygen poor. And so then with the interaction with your more reduced mantle would give you a lot of methane in the atmosphere, and you could probe the carbon from there. So now let's look at the data. But first, a disclaimer that when these observations were planned, we didn't know that the features we'd be looking for would be like 20 to 25 ppm, because this is like a very small, like a very metal-rich atmosphere. So this is what it looks like. So this is the nearest data that I showed you before, but kind of zoomed in, because we're really looking for these very small features. And this is what the near-spec data tells us. We're not seeing any strong molecular detection. But I think what is most interesting is kind of the broad conclusions we're drawing from the upper limits we can put still on the carbon content. In particular, we only find upper limits on the CO2 to water and methane to water ratios. And what that tells us is that this atmosphere seems surprisingly carbon poor. That's not something that you would expect if you had an interaction with a magma ocean. This is actually a very reliable prediction from all models of interior atmosphere interactions that you should have actually elevated atmospheric C/H ratios if you have a magma ocean, because so much of the water partitions inside. And so in this magma ocean hypothesis, another challenge is explaining the low density of GJ98270 that implies a high, well, a relatively high, let's say, envelope mass fraction that could be up to some tens of %, with a high water inventory, because again, you would have more of the hydrogen in the atmosphere and the water would preferentially partition inside. But these models here don't consider fractionated mass loss, and so we could just say maybe just a lot of the hydrogen has been lost, and kind of fractionally over time, this planet is just enriched in water. But I would like to end with asking a fundamental question of whether there is even a magma ocean on this planet. And so now we actually have some of the ingredients that we need to make a first evaluation of that. First, we have some information about the atmospheric composition that we can use to break some of these degeneracies. Second, we can place a prior on the composition of the interior with a new characterization that we have of the elemental abundances of the star. And putting all of this together, knowing the mass, radius, and irradiation of this planet, we can have some idea of the extent of its envelope, all the way to the boundary with the mantle. And so now if we look in phase space of pressure and temperature, what that would look like, where the atmosphere temperature would be in blue, and the interior is just an isotherm over here, you can see that actually the pressures are high enough that even if maybe when the planet formed and was hotter, you could have a magma ocean, it's very plausible that today you don't, and that could actually explain why you could have a water-rich atmosphere if a lot of the water was released into the atmosphere. So I'll leave up my conclusion slides, but I think we can learn a lot from small sub-Neptunes on the volatile budgets and the evolutionary processes that actually sculpt the population of rocky planets as well. And there's a lot to be learned if we have access to both oxygen and carbon-bearing species. And finally, we really need to do, for more planets, kind of detailed modeling of the atmosphere and interior to figure out on which we should actually expect magma oceans. Thank you.
Right. Any questions? Mercedes?
Mercedes Lopez-Morales, Space Telescope Science Institute. Awesome talk. To constrain the formal structure, you said that you have information from the Planetary of the stars.
Yeah.
But are you okay with the precision in the mass measurements? Because we all say,
yeah,
precision. Is that enough?
It is true. It is not a very precise mass, and it kind of has gotten worse over the years as because it looks like the more recent papers have gotten more conservative with what you can do with even more data. But I would say that for this planet, it doesn't look like we're really limited by the mass precision. It's kind of big enough that the radius is the main thing that you care about. I think the main thing is, again, assuming a prior on the interior composition based on the star isn't necessarily true or right. It's just kind of a way of kind of restricting your parameter space.
And is it true, so you just said for this planet, can we assume that that's the case for all the other planets? The reason why I'm asking is that we're spending a lot of time getting rid of velocities trying to get precisions of 2%. And if people like you come and tell us, guys, 20% precision is good enough.
Okay, I think there was a paper, I don't know, maybe it was just for rocky planets, but there was a paper by Diana Valencia's group last year that was talking about kind of the mass precision that you need to get some precision on the composition. I think they were talking about core mass fractions. I don't know if they looked into sub-Neptunes, but I think it would be interesting just kind of at the population level to have it. Yeah. Sort of okay, yeah. To have an idea of that. I don't have a good handle on that, but yeah, if you have a specific planet you're curious about, I can check that.
Is it quick?
There might not be a quick answer, but I'll make the question quick. Have you considered A, disequilibrium chemistry, and B, gravitational fractionation in thinking about whether or not what JWST sees is actually reflective of the interior, deeper atmosphere? CO2 is a lot heavier than water.
Yeah. This isn't something that I've particularly thought about for this planet, because the atmosphere is kind of thin enough that I was hoping that we could make these assumptions, but I'll think about that. I'll think about whether that's the case. For sure. Because you could say, okay, you would maybe expect methane because of the temperature if you didn't have mixing, but at the same time, it's such a high metallicity that, maybe not. Maybe it's not just a scaled, hydrogen ball with more metals. So I'm kind of thinking about these beasts a little differently. But I'll give that some thought.
Let's take our speaker.
Can you hear me okay? Okay. Yeah, so hello everyone, I'm Brendan Park-Coy. I'm a third-year PhD student, also at UChicago. And today I'm excited to talk about what we can learn from population level analysis of rocky planet thermal emission data. So one of the really exciting questions that we're starting to be able to answer with JWST is whether sort of this dividing cosmic shoreline concept calibrated from the solar system is applicable to rocky planets around other stars. Almost 2,000 hours of JWST time have been invested in rocky planet atmosphere observations. So understanding what they can tell us, even in cases of null detections, is really crucial. But how do we actually find these atmospheres? So Qiao talked about this a little bit earlier, but one particularly powerful method is by directly measuring the thermal emission coming from the planet. And this can work by either constraining the amount of heat redistributed to the night side from a thick atmosphere, or by targeting key absorption features. These observations also have the unique potential to probe the surface composition. And this is a technique commonly used in solar system investigations. However, despite thousands of hours of observations with JWST, the search for these kinds of atmospheres has yet to provide good evidence for one. All emission observations thus far have been sort of 1 sigma consistent with the bare rock, or complicated by very strong systematics. What these observations have allowed for are precise measurements of the dayside temperatures of these planets, which can be used to place limits on both the surface and atmospheric composition. So this figure here shows how 5 eclipses of TRAPPIST-1b were able to rule out even a thin Mars-like CO2-dominated atmosphere. However, these observations some of them are still ambiguous, and atmospheres remain possible in some cases. So a potential avenue to a less ambiguous interpretation is by analyzing all these observations on the population level to explain potential trends in key planet parameters. So in this work, we did this by homogeneously rederiving this sort of brightness temperature ratio. So Qiao introduced this earlier, but essentially this is the measured dayside temperature compared to what we would expect from just a 0 albedo black body, or maybe a bare rock. And we can see that a value near 1 is pretty indicative that there's probably not an atmosphere, but its dependence on bond albedo and heat redistribution imply that as you go down, the evidence for the atmosphere becomes more likely. And what we sort of found was that while these observations are all individually consistent with the bare rock null hypothesis, when we analyze them together, they show a striking trend in increasing brightness temperature ratio with increasing substellar temperature. And what this trend implies is sort of temperature-dependent processes that alter the inferred albedo of these planets, darkening those that are closer in and hotter. So one potential explanation for this trend is space weathering. So this is a process that occurs when iron locked in surface silicates here is altered and precipitates out as these extremely dark nanometer-sized metallic iron particles. And we can see that here kind of nicely with a real microscopic image of lunar regolith showing the dark space-weathered rim. So space weathering is thought to be primarily regulated by both stellar winds and micrometeorite impacts. And we think that these processes are probably much more important or much more violent on these rocky planets around small mass stars. So due to its potential scaling with stellar wind strength, it's reasonable to assume that these closer in, more highly irradiated planets are more affected by this mechanism, leading to quicker darkening of their surfaces. And this is actually something that we can see pretty nicely in the solar system. Both main belt asteroids and near-Earth asteroids that orbit in closer to the sun show higher evidence for space weathering, as seen here. So we can see here that a single sort of regolith model isn't really sufficient in explaining the observed trend in brightness temperature ratio. But increasing space weathering on closer in, hotter planets can naturally explain sort of this 1D trend in brightness temperature ratio. And while all of these planets lack evidence for thick atmospheres, we can't really rule out the possibility of thin or tenuous atmospheres that have been revived by late-stage volcanism or perhaps cometary impacts. In this case, the choice of instrument has a large role in your interpretation of the brightness-temperature ratio. So here I'm showing a Venus-like composition and its effects on the brightness-temperature ratio that you would see in MIRI LRS and MIRI 1500W. Since 15 micron covers this very prominent absorption feature of CO2, the effects of atmospheres here are more dramatic. But when we look at these planets in sort of consistent pressure upper limit space, these colder planets become more consistent with the possibility of thin, possibly millibar or Mars-like atmospheres. And this makes sense because they receive orders of magnitude less atmospheric escape fluxes than these closer in orbiting planets. However, previous work has shown that these sorts of atmospheres on tidally locked planets are very inefficient at redistributing heat to their night side, and they're susceptible to something known as atmospheric collapse, where volatiles like CO2 can freeze out completely on the night side. Thus, a geological explanation for this trend seems more likely. So again, we can see here that most rocky planets orbiting small M stars are sort of consistent with this bare rock picture that's been emerging. However, large-scale surveys like the Rocky Worlds CDT are aimed at figuring out whether this trend holds for colder, even less irradiated planets. In addition, the recent detection of thick atmospheres on some of the most irradiated planets around larger mass stars have challenged sort of this cosmic shoreline concept that predicts that they wouldn't be able to have held on to substantial atmospheres. It's still pretty unclear what these atmospheres are made out of. Were they accreted from primordial atmospheres, or are they simply atmospheres that are replenished by constant vaporization of their surfaces? And is there sort of a critical transition temperature where these kinds of atmospheres become common? So I'm super excited to be part of a JWST Cycle 3 program led by Megan, aimed at directly characterizing this transition from bare rock to potentially thick atmosphere, known as lava lamps. So this is kind of the plot I was showing earlier with a little bit more observations from the hot rock survey, but showing how most planets orbiting M stars seem to be consistent with sort of this bare rock null hypothesis. However, when we start looking at the hottest planets past a substellar temperature of about 2,500 Kelvin, much hotter than the melting point of rock, we start to see potentially evidence for a population of atmospheres. And the lava lamp survey is using single eclipses of 10 different ultra-hot rocky planets within this crucial temperature range to try to accurately characterize this transition. And I want to emphasize that these results are pretty preliminary. I realized after I made these slides that these talks are going to go on YouTube anyway, but nevertheless. Yeah, so you can see here. So here I'm plotting all of the previous observations and then our lava lamp sample in red. And you can see here that we're sort of beautifully actually capturing this transition from a bare rock or thin atmosphere like thermal emission to potentially a thick atmosphere. And it does seem like maybe there's sort of this critical transition temperature of about 2,500 Kelvin when these atmospheres start becoming common. However, while all of these planets show evidence for low brightness temperature ratios, it's actually pretty unclear what their atmospheres are made out of. Silicate vapor pressure equilibrium only predicts about 10 to maybe 100 millibar atmospheres on these planets, which is not enough to show sort of that full heat redistribution value that we're seeing for their brightness temperatures. So there must be something else going on here. So these could be reflective silicate clouds. We've seen a hot Neptune, LTT 9779b, around the same temperature as these targets actually, with extremely reflective silicate clouds and a very high bond albedo that could help explain this. In addition, these could be just very fractionated, shiny magma pools that are rich in very refractory elements like potentially calcium and aluminum. We also don't really understand how the silicate vapor feedback should work on these planets. Silicate vapor is theorized to be a very strong optical absorber where most of these planets' thermal emission is being radiated. So it's possible that this greenhouse feedback can lead to sort of runaway vaporization of more and more silicate vapor. But lastly, these planets might have actually just formed extremely volatile rich and migrated inward, losing most of their atmospheres, but retaining these heavier volatiles like CO2 and potentially water. And we saw a talk earlier this week by Joanna showing how some observations are consistent, especially with TOI 561b of this picture. So yeah, to summarize, both the coldest and the hottest planets observed by JWST in thermal emission show strong trends in their brightness temperature ratio as a function of their substellar temperature. While the colder planets seem to be more geological in origin, the hotter planets show very compelling evidence for a population of atmospheres on these ultra-hot lava worlds. And with that, I'll just leave this slide up and happy to take any questions.
Any questions?
This might be slightly out of your wheelhouse, but in the solar system, we're able to use like the thermal diffusion timescale to measure the thickness of crust. Is there any possibility of doing this for these like no atmosphere planets?
My gut feeling is no. The best thing we can do with a lot of these planets, especially the colder ones, we're only getting photometric observations. So we can maybe say something about their overall bond albedo. But my gut feeling is no. For some of the mid-temperature planets, we can actually get pretty precise spectra that might be able to say something about their surface composition through this like SIO stretch feature. But yeah, we thought about this a little bit, and I don't know if we can say anything about crustal thickness necessarily.
I'm like past MIT. I was curious with like those 4 options that you have. Do you have ideas of like what's the next step to differentiate between those options, or what observables you need to start breaking those degeneracies?
Yeah. So I mean, more observations always help. This survey was designed to go wide and not deep. So while we do have spectra for these targets, they're very low precision. And doing something like a survey of going in deep on a couple of these targets that we know have atmospheres would be very helpful in determining whether they have, for example, CO2 in their atmosphere, or whether theoretically there's some features of SIO and SIO2. They're very small, but potentially we could see those and characterize what they're actually made out of.
Peter?
Yeah, great talk. What's the range in stellar types here? I mean, I assume most of these are not all M dwarfs, but
yeah,
we're talking about from late to early, or mostly.
Yeah, so it's actually kind of a gradient here that you can a little bit see by eye. So all of these black points on the left side are M dwarfs. These 2 are actually M dwarfs as well. I think these 4 are Ks, and then the last 2 are potentially Gs. It just becomes an issue because you can't have a planet at this temperature without being like tidally disrupted. So that's kind of why you're seeing that. But yeah, the ones with atmospheres are all Ks and Gs. So there might be some argument of initial volatile inventory being a function of like what stellar type you are. But yeah.
All right, let's thank our speaker.
Hello. Can you hear me all right? Yeah. So it's a great pleasure to give the final talk of this brilliant workshop. It's also a lot of pressure to follow these great talks. So I'll be suggesting some rules for retaining an atmosphere on M-dwarf rocky planets based on the known physics of the escape of secondary atmospheres. The Kepler Space Telescope launched in 2009, and it brought us news of bimodality in the radius period distribution of small exoplanets. Super-Earths lose their primordial envelope, being on shorter orbital periods and being more irradiated, while sub-Neptunes on longer orbital periods are able to retain their atmospheres, puffing their radius up with an evolutionary dearth of exoplanets in between at about 1 Earth radii. And this was actually predicted by energy-limited mass loss models of primordial hydrogen. Then in 2021, the James Webb Space Telescope was launched, and over the previous few years has been revealing a picture of about almost a dozen now transmission and emission measurements that give us evidence for bare rocky planets. There are some exceptions to this rule, as Brandon just mentioned, but broadly it's in keeping with the cosmic shoreline hypothesis that the greater the radiation dose from the host star and the smaller the planet's gravity, the less well it's able to hold onto an atmosphere. And this talk is mainly going to focus on secondary atmospheres, exo-Earth and exo-Venus, carbon dioxide dominated, nitrogen dominated. But whether we're talking about primary or secondary atmospheres, the classic form of photoevaporation takes the form of Parker's transonic hydrodynamic wind, which is lucky for us because the momentum equation has a critical point in it that's very constraining, as we heard from Ruth. So when you reach sound speed, your velocity has to equal about half the escape velocity. And the sound speed is proportional to the square root of the temperature over the local mean molecular weight of the atmosphere. So for a greater escape velocity, you need a hotter upper atmosphere. And for a higher mean molecular weight, you also need a hotter upper atmosphere. So you can get very quickly into 10,000 Kelvin or 20,000 Kelvin atmospheres required. We also get a constraint from the transonic rule on the scale height of the atmosphere, because in order to go sonic, you need the pressure gradient force to accelerate you there, so you need to remain collisional out to the sonic point, which means your sonic density has to be greater than your exobase density. Also constraining the temperature and the mean molecular weight. So our first rule is that the higher the mean molecular weight, the greater the irradiation needed to drive transonic escape. And we get even more info from the transonic rule from if we have the speed from the sonic point and we have the density there, we can get the mass loss rate. And so for secondary atmospheres, transonic escape rates are at least 1,000 bars per billion years. And we can compare that to other mass loss mechanisms such as stellar wind erosion, and the published results in similar XUV intense environments find less than a bar per billion years. And so when this threshold in irradiation needed to drive transonic escape is exceeded, it exceeds all other mass loss. So it's the first port of call if you want to assess your prior on whether we should retain an atmosphere. Do we have enough irradiation to drive transonic escape? So even without knowing this, we just want to minimize ionizing irradiation. It strips away atmosphere, so we want to be on a cooler orbit around a higher mass star, something that started off slowly rotating and hopefully weaker flares. But how low do we need to go to be able to retain a secondary atmosphere? So this figure from David Fleming, I've lost the citation here, but 2019, shows the XUV environment around TRAPPIST-1. I think this has been updated to be even more extreme recently, but we can see that for TRAPPIST-1b, 100 million years after formation, it received perhaps 10,000 times present Earth levels of ionizing irradiation, FXUV Earth. And even after a billion years, it still receives thousands of times XUV Earth. Even for TRAPPIST-1e out in the habitable zone, we're talking about early on thousands of times XUV and hundreds of times present-day Earth XUV today. So these these ionizing radiation levels are unprecedented, and not many simulations have been run for secondary atmospheres to this level. We can compare to the young sun, which also had enhanced XUV, but for a much shorter time, which was about 100 times present Earth levels. What is the threshold for hydrodynamic escape? Well, the first models for this came from Feng Tian in 2008 and 2009. He ran a very sophisticated hydrodynamic thermosphere model and found for only 10 times FXUV Earth, we get a transition into a hydrodynamic blow-off state. And so this, from this result, unless the planet started, absurdly volatile rich, if we're thinking about secondary atmospheres, then this is very pessimistic for M dwarfs. Almost none of the planets we found around M dwarfs would ever reach below this level. So no secondary atmospheres would be retained. But in 2022, after the launch of the James Webb Space Telescope, Akifumi Nakayama showed how electron impact excitation of the low-lying excited states of atoms can really efficiently cool an upper atmosphere. And so they revised this estimate for hydrodynamic outflow to 1,000 times present Earth levels of irradiation. And so it's through this efficient atomic line cooling of metals that M-dwarf planets have a hope in hell of retaining secondary atmospheres. But actually, the planets still receive often more than this irradiation for some part of their lifetime, and there's now been modeling since, although not very much. So what does this picture mean for the size range of rocky planets? That's what my thesis work focused on. And so we investigated this balance of XUV, high mean molecular weight, and line cooling for the size range of rocky exoplanets. So Nakayama only looks at an Earth-like planet. And what we want to compare is the temperatures we need in the upper atmosphere for transonic escape to the excitation temperatures of the first and second excited states of nitrogen and carbon and oxygen. And we can see that their energy levels are around 2 to 4 electron volts. An electron volt is around 10,000 Kelvin. And so we need at least several thousand Kelvin to start exciting these levels appreciably. So with the transonic rule again, for Mars, the upper atmosphere only needs to be kind of 4,000 Kelvin or less, and we find that with 50 times FXUV Earth, you can get transonic outflow, you can get subsonic outflow at even less than that. Earth has a 5 times greater gravitational binding from Mars, and so we're pushed into a regime where we need about 20,000 Kelvin in the upper atmosphere. And this is when the atomic line cooling starts to be efficient, although we think you can still have weakly ionized outflow, so it's not the most efficient it can be. So we estimate maybe 400 times present Earth levels of ionizing irradiation. You can drive transonic photoevaporation. And so this threshold's high enough that you start to have retention being plausible for some Earth-sized rocky planets around M dwarfs. Even greater gravity, the super-Earths, require temperatures so high that you probably can't get weakly ionized outflow at all. You need fully ionized global outflow, which is a kind of novel astrophysical flow of metals. And so the reason you need to be ionized is because the electrons drag out the ions and half the effective mean molecular weight of your atmosphere. And if you include this effect, then for maybe 1,000 times FXUV Earth, you can have outflow from some super-Earths. So the super-Earths are very much the best targets. And so our final rule is that atomic line cooling hardly protects sub-Earths, but is very protective for super-Earths. And so this is even more non-linear than the cosmic shoreline. Xuan talked about this in Wednesday's session. She also showed that volatile abundance is game-changing, but for classic terrestrial atmospheres, the physics of secondary escape is still very important. And so based on the transonic rule and these limits, we can make some predictions. The first is that the sub-Earth TRAPPIST-1e is not expected to resist photoevaporation. Atomic line cooling won't be very efficient. Its gravity is significantly lower than Earth's, and so you should go back to maybe Tian's threshold, and so it's way above that threshold for all of its lifetime. Never say never, late delivery by comets, all these things could mean perhaps it has one. But that's, I think, the best prediction from secondary atmosphere escape. For super-Earths, there's much more wriggle room. We actually heard now from Colin that LHS 1140b probably does have an atmosphere, maybe helium dominated. We already probably knew that from the density, but if it was a rocky density, then we would still expect it to retain a secondary atmosphere because it's out in the habitable zone and it receives less than this kind of 100 times or 1,000 times level currently, and it probably received less than the 1,000 times level in the saturated phase. So there's a lot going for it. That's got Rocky Worlds DDT and some transmission observations coming up. Another good super Earth is 2I771b, which does have a rocky density. So perhaps this is a good target for a classic secondary atmosphere, perhaps an exovenus. There are also exceptions to these rules. For example, if we have the most inactive M dwarf we can ever find, then that's really going to help volcanic revival in the main sequence. Once the XUV flux drops below this threshold we've discussed, then volcanism at 10 bars per gigayear can often exceed non-thermal loss. And so when you don't have transonic loss, you can revive an atmosphere. And there's also possibly exotic new planets being discovered. Coupled atmosphere interior evolution modeling by Harrison Nichols showed that perhaps L9859d is this sulfur world starting with 1 weight percent or 2 weight percent in sulfur, and then you're starting with so many metal volatiles that you can retain your atmosphere regardless. How much time is that? Okay. So there's lots of open questions still with secondary atmospheric escape, so it's going to need a community effort, especially for this global ion outflow from super Earths. It's not been modeled hardly at all. You can come see my poster still at lunch on direct simulation of this subsonic outflow, where the threshold is slightly lower than the transonic threshold, but it's still high enough to exceed any non-thermal loss, and maybe the actual process that's determining the cosmic shoreline for super Earths. Photochemistry could also change a lot of these results. On TRAPPIST, the UV is very low, so perhaps that could give you a way of retaining some atmospheres. It's about 100 times lower compared to the XUV. And then I'll leave up my takeaways. Thank you.
Any questions? Come on, it's the last talk, guys. Yeah.
So I've been taking notes this whole conference, and there were talks that discussed the TRAPPIST-1 could potentially retain a substantial volatile. I think it was a paper actually, Kimura and Koma 2022. There were 2 talks that, including yours, the first one was on a talk. I think it's a work by Gianelli that predicts that TRAPPIST-1e should not have an atmosphere because of tectonic. So what? But there are observations of TRAPPIST-1e, the Kevin discussed ceremony. So how close are we on solving the mystery of TRAPPIST-1e? Is it what is going to be the final nail in the coffin? Is it going to be the theory of both your observation?
I think they can work together in synergy. For example, it would be great if the models for escape were good enough that they could inform a prior on whether you expect an atmosphere to be there or not. Obviously, there's degeneracy with the volatile abundance you start with, so that could then enhance the power of the observations. And it would also then, you could feed that back into more predictions. But we only have this smattering of papers like Feng Tian, Colin Johnstone, and so on. So we do need more models, especially for the super Earths. I think for sub-Earth planets, it's relatively well understood. There could always be some other mechanism where things cool. Yeah. So if TRAPPIST-1e was a super Earth, then they could all be to play for. In terms of an atmosphere, it really makes a huge difference.
Madeline Bruns, Santa Cruz. Is it the atomic line cooling more effective in the outflow at suppressing the outflow, or were they looking at the lower atmosphere cooling?
Yes, so they find a kind of full photodissociation front and then a full ionization front. And once you get into the atomic region, your atmosphere in the Nakayama simulations in the hydrostatic model thermostats to around 5,000 Kelvin very strongly. So they change the XUV by a factor of 20, and it remains at around 5,000 Kelvin in the upper atmosphere. But their upper boundary condition, they don't account for ionization, even though you're fully ionized, or they don't account for it fully. For example, this ambipolar electrostatic field. So that's why there's a revision again. But there's more to do, and magnetic fields impact that ambipolar electrostatic field. So yeah, for Earth-sized planets, again, it's actually in this sweet spot where the atomic line cooling starts to be really important. So another sweet spot for Earth.
All right, and with that, we're going to say thank you to all of our Session 7 speakers. Go eat lunch. Are there any announcements?
No, well, we should come back at 1:15.
Yes, please come back at 1:15.